In the previous video in this playlist, I talked about what is a vector, how to represent a vector geometrically and algebraically, then vector addition and scalar multiplication, vector subtraction, vector length or magnitude, and unit vector. In this video, I'll talk about vector space and the rules of vector space. A vector space is a collection or set of vectors. The most common vector spaces we know about are the R vector spaces like R1, R2, R3, Rn. Here Rn means it's a vector space that contains all the vectors where each vector has n components and each component is a real value. If let's say v1, v2 till vn, then vi is a real value for all I in 1 to n. Now what is R1? R1 is a line, like it contains all the vectors with one dimension, or you can say the point vectors, and this line is the R1 vector space. Next, R2. Here we have this x-axis and y-axis, and this is the xy plane. And in this plane, we can have lots of vectors, and each vector in this space will have two components. So this is R2. All vectors with two dimension, and each component is a real value. Next is R3. Here we have x-axis, y-axis, and this is xy plane, and we have one more dimension, z dimension. The vectors in this space will have three components. Now beyond three dimensions, it's difficult to visualize, but we got the idea what do we mean by a vector space. Now a vector space is a set of vectors that satisfy certain properties while performing vector addition and scalar multiplication. Consider this capital V, this is a vector space, and u and v, these are two vectors in this vector space. Then if this capital V, this is a vector space, then u plus v also should be in this vector space. Consider this is R2. This is R2 explain x-axis and y-axis, and we have two vectors, this is u and this is v. U and v belongs to this R2. Now let's add u plus v. For that we'll move v and place it at the tip of u, right? And then we'll get our resultant vector. This is u plus v, and this is also a part of R2, right? This u plus v also belongs to R2. So R2 is a vector space. But let's say one more set of vectors where x, y greater than equals to 0. Now if x multiplied by y is greater than equals to 0, that means x and y both should be positive. So this is the space. Also x, y both can be negative. So this is the space, right? So now if let's take two vectors in this set, one is this one and another one is this one. Let's add these two. For that we'll move the second vector and place it at the tip of the first one, right? And This is our resultant vector. Clearly, this resultant vector, this is not part of this set. So this set is not a vector space. And this property is called closed under addition. If we add two vectors, the resultant vector should also be inside the vector space. Next property is, consider this capital V is a vector space and U, V are two vectors in this space, then U plus V equals to V plus U. Now here, let's say this is U, this is V. Here in left side will perform U plus V and in right side will perform V plus U. Now add U plus V. For that, we'll move V and place it at the tip of U, right? And then we'll get our resultant U plus V is this one. I'm not drawing the line properly, but you are getting the idea, right? So this is U plus V, and in the right side we'll add V plus U, means we'll move U and place it at the tip of V, and this is our resulting vector V plus U, and this U plus V and V plus U are same and it should be same. This property is called commutative nature of addition. Now next, consider V, this capital V is a vector space and U, V, W, these are three vectors in this space. Then U plus V plus W equals to U plus V plus W. So in the left hand side we perform this and in the right hand side we will perform this. So consider this is U, this is V and this is W and this is W, this is U and this is V. So here we'll perform V plus W first. Let's do that. So this is V plus W. Now we'll add U and V plus W, right? We'll move V plus W and place it here. And our resultant vector will be this one. In the right hand side, we'll perform U plus V first. So we'll move V and place it here. Now this is our U plus V. This is U plus V and with that we'll add W. So let's add W. So our resultant vector will be this one. And this left hand side and right hand side, you see these two vectors should be same. This is called associative nature of addition. Next is, in any vector space, we should have a zero vector such that 0 plus U, any vector, should be U, right? And the zero vector will be at this origin. This is xy plane and this should have 0, 0, 2 components. For any n dimensional vector, zero vector will be n zeros, and if we add any n dimensional vector with that, we'll get the same vector. This property is called additive identity. So this 0 is additive identity. Next, in any vector space, for all U in that vector space, U plus minus U equals to 0, that additive identity. Now consider this is U, then this is minus U. right? So how do we add u and minus u? So from the tip of u will move at the direction of minus u, right? So like this, and will reach at 0 vector, right? So this is called additive inverse. So this minus u, this is additive inverse. Next is, consider this capital V, this is a vector space and U is one vector in that space. C is one scalar. C is in R means C is a scalar. Then CU should belong to this vector space. So consider this vector, right? So if we scale that vector with any scalar, let's say if we stretch it, or we can squeeze it, or if the scalar is negative we'll flip it, or we can flip and stretch, or flip and squeeze. So if it is an R2, then all the scalar multiples of that vector also in R2, right? So, but let's say one more example. Let's say V is a set of vectors where x, y is vectors where x greater than equals to 0 and y greater than equals to 0, right? So in that case x, y both greater than equals to 0 means we are talking about this region, right? So in that case you take any vector in this region. If you multiply it with a positive scalar, of course it will increase, or like it will stretch or squeeze. But if you multiply it with a negative scalar, the result will be outside that space, right? So this set, this is not a vector space. This property is called closed under scalar multiplication. The vector scalar multiplication should be closed inside the vector space. Next, consider u, v are two vectors in this vector space capital V, and c is a scalar. Then c multiplied by u plus v equals to cu plus cv. Consider this is u, this is v, and in the left hand side what we are doing is we are adding u plus v first, then we are multiplying that resultant vector with this with c. Consider c is 2, and first we will add u and v. So we'll move v and place it at the tip of u. So this is u plus v, and then we are stretching it 2 times. Right side what we are doing is we are stretching both the vectors 2 times. This is like this and this also like this. Then after that we are adding these two vectors. So for that we'll move this one here, and our resultant vector will be this one. So definitely this one and this one should be same. This property is called distributive nature of elements to scalar. Next, if U is a vector in the vector space and C, D are two scalars, then C plus D U equals to Cu plus Du. Consider C is 2, T is minus 3, and this is U. Now C plus D is minus 1, right? So if you do this left hand side, this is basically minus 1 u, and right side is 2u plus minus 3 u. So in the left hand side we'll do minus 1 u means this is just this. In the right hand side, what we are doing is we are first calculating 2u, this is 2u, and minus 3u is this one, let's say. Then 2u plus minus 3u is from here will move direction and will reach here. So this is our resultant vectors. And this one should be same. This property is called distributive nature of scalars to elements. Next, consider you are having this capital V vector space and U is one vector, C, D are two scalars. Now we have in that case C multiplied by du equals to CDU. So if C is 2, D is 3, then in that case in the left side what we are doing is we are first multiplying du this is stretched 3 times, so this is du, and then this one is stretched 2 times, means like this. And in the right hand side what we are doing is we are multiplying this one 6 times. So again will be reaching at the same position. So this one and this one should be same. This is called multiplicative associative property. And the last one, in any vector space there should be one identity vector 1 such that 1 multiplied by u is u. So this is called multiplicative identity. And these are all the rules a vector space must satisfy. So this is what I wanted to discuss about vector space. If you find this video useful, please like, subscribe and let me know about your feedbacks in the comment section.